Are you? Are you?
Are you worried about your acid and base part 3 test?
Well, worry no more, because I'm going to give you the best tips on how to do well on this test.
This test is harder than the other ones. It combines 3 units in one.
But I got 110% on this test, and so can you.
I'll be honest, even if I did know what was on the test, I'm not allowed to tell you. But what I can do is make sure you have some certain important topics down that most people miss.
Because you really need an extending understanding of this unit to do well on this test. So let's go back to my desk. Okay, so you just finished studying your 3 note packages, and you think you're ready for a test. But let me tell you, you're not ready for a test until you watch this video. Because I'm going to give you some final remarks and reminders before you take the test, and I guarantee it will help. The first thing is, make sure you read every single page of your notes, even if it seems unimportant. Because there could be some very specific examples that are based off of these specific unimportant pages. Even if the content on that page seems unrelated to acid and bases that you're learning right now, it will help if you read them all. I'm not kidding. Even if you have a biology chapter in your acid and base notes, you should still read it. Next, I want to quickly go over the relative pH at the equivalence point for different titrations. Starting with a strong acid titrated with a strong base, that's going to give you a pH of 7 at the equivalence point because it'll be neutral when they neutralize each other. When you titrate a strong acid with a weak base, your pH at the equivalence point is going to be less than 7. And this is because you're going to create a salt left over that's actually going to hydrolyze and form an acidic solution, like we learned in the last video. For example, if we have a strong acid, HCl, titrating with our NH3, a weak base, that's going to form NH4Cl. And as you know, this is a salt, right? It's going to dissociate into NH4 plus and Cl minus. And remember that our NH4 plus, that's one of our Fab4s, so that's going to form an acidic solution. So initially this part, that's going to become neutral, right? pH 7. But then your resulting salt here is going to make it acidic. So that's why your pH is going to be less than 7. Same thing goes for weak acid plus strong base. It's going to result in a pH slightly greater than 7. And that is because you're going to form another salt, but this time the salt's going to form a basic solution. Finally, for weak acid and weak base, this one really depends on if your acid is stronger or is your base stronger. So you have to compare Ka versus Kb. And if the stronger acid, then you have pH less than 7. If it's a stronger base, then pH greater than 7. And something I forgot to mention in my past video is, why do we actually compare our Ka and Kb? Let's take, for example, HSO3-. This is amphiprotic, so it could be an acid or a base. Let's write the equations showing it being an acid and a base. So as an acid, you got HSO3- plus water. Since it's an acid, it's going to be donating. So we have SO3, 2- plus hydronium. Now as a base, it's going to be accepting. And I will write out the Ka and Kb values. For Kb, that has to be our Kw divided by Ka. So that's 1.0 times 10 to the negative 14 divided by our Ka, which is 1.5 times 10 to the negative 2. And that's going to give us a KB of 6.67 times 10 to the negative 13. So now we compare Ka and Kb. But why do we actually do this? Remember our equilibrium constant expression? It's going to be equal to our products over reactants. And a bigger K, so a bigger equilibrium constant, means that you have more products. So more products and less reactants. What does that mean? That means that in terms of acid and bases, you get more of your hydronium or hydroxide. So a bigger Ka means you have more of this than whatever's on this side. Same for a bigger Kb. And we compare how big our Ka and Kb is, because that shows us, do we have more hydroxide being made, or do we have more hydronium being made? Let's say theoretically our HSO3 minus here, let's say it wanted to be an acid more than it wanted to be a base. So as an acid, it would make more of these products over here than if it were a base to make these products. So the main reason here is a bigger K means bigger products. And having more products means that it will tend towards being an acid or base more. Hopefully that makes sense. Okay, next, something that some of you might not be able to do right now is compare concentration of ions, which is a Chem 11 unit. Let's say you had NaCl and it's 1 molar. And we want to find the concentration of Cl minus. We're going to first dissociate our NaCl into Na plus and Cl minus. And because it's a 1 to 1 to 1 ratio, it's just going to be 1.0 molar for our Cl. And same with our Na plus. But if we had a different ratio, for example, MgCl2, and it's going to be 2.0 molar, and we want to find concentration of Cl minus. We're dissociated again, so MgCl2 is going to become Mg and 2 chlorines, and because you have a 2 here, we have to multiply the original concentration by 2, because for every 1 mole of our magnesium chloride, it's gonna dissociate into 2 moles of chlorine. I forgot to write my signs. Let me write that. Okay. So our chlorine concentration is just going to be equal to 2 times 2 equal to 4.0 molar. Next, let's look at indicators. How do we pick an appropriate indicator for a titration? Well, we know that for an indicator, at the transition point, our pKa of the indicator is going to be equal to our pH. And since we want our indicator to change colors at the equivalence point, or as close as possible, we want to find an indicator where the pKa is going to be similar to the pH of our transition point. So let's say we were titrating a weak acid and a strong base. And our equivalence point, pH, is going to be equal to 8. We want to find an indicator where the pKa is as close to 8 as possible, so that when we are titrating and we reach our pH of 8, which is the equivalence point, the indicator will change colors and let us know that we've reached that point. Now here's something that most people miss. Did you know that thymol blue has 2 transition points? It has one from 1.2 to 2.8 and one from 8.0 to 9.6. That means that at low pHs, it's going to go from red to yellow, but at a higher pH, it's going to go from yellow to blue. And that's kind of like a special case because it's actually diprotic, so it has 2 transition points. Next, we're going to look at our polyprotic titrations. Let's say we had a polyprotic acid, so H3PO4. And after its first equivalence point, it's going to turn into H2PO4 minus. And after its second transition point, it's going to become HPO42 minus. And then third transition point, or equivalence point, it's going to be PO43 minus. And what this means is if they were asking us to find to write the equation for the, for example, third equivalence point, here's how we would do it. H3PO4. And since we're going to go to its third equivalence point, right? So it's going to be reacting with water 3 times. So we're going to add 3 H2Os to form 3 hydroniums and our PO4 3 minus. So basically what's happening here is it's being neutralized 3 times. The protons have been pulled off of our H3PO4 3 times, and it results in this. On the titration curve, it will look something like this. 1, 2, 3. And that's our first equivalence, second, and third. Speaking of titration curves, I'm sure you've seen something like this before. But have you ever seen a titration curve with a buffer? Well, what do we know about buffers? We know that they resist changes in pH, right? So as reaction progress goes, or as we add more base, for example, let's say this is pH over addition of base, we would expect an addition of base to cause the pH to go up, right? But if there was a buffer, if we keep adding base, it's going to resist a change in pH for a while. Let's say that we have a buffer present at this point here. Then it would look something like this. We would add base, but it wouldn't go up yet. And then once the buffer wears off, then it would go up. And that's what it would look like if there was a buffer in a titration curve. Next, obviously, if the questions on the test were like the ones that you prepared for, it'd be too easy, right? So what I notice that Mr. Shim does is that he pulls things from other topics, possibly in the past, and adds it to your current unit. And he makes you apply topics from different units to get the right answer. For example, remember our net ionic and complete ionic equations? Those aren't touched on a lot in acid and bases, but I feel like they could be applied on the test, possibly. I can't say for sure. Anyways, let's quickly go over some net ionic and complete ionic equations for titrations. Let's say HCl plus NaOH. That's going to form H2O and NaCl. For net ionic, we dissociate everything that we can. We know we could dissociate H and Cl minus because HCl, it's a strong acid, right? So it's going to dissociate fully. Same with NaOH. Water we can't, and then Na plus and Cl minus. So that's our net ionic. And we can cancel out anything that's on both sides. For example, Cl minus, Na plus, and we're left with H plus OH minus becomes H2O. That's our net ionic equation. And this is actually the same for all strong acid, strong base reactions. This is your net ionic. But what if you had a weak acid? So say you were combining acetic acid with NaOH. That's going to become NaCH3COO and H2O. Now to get our complete ionic, we're going to dissociate everything. But we can't dissociate our acetic acid fully because we know it's a weak acid. So it's not going to go 100% into its ions. That's why we're going to leave it. We can dissociate our NaOH. We just dissociate this one. And water. Now we can cancel our sodium, and we're left with and that's how you do complete and net ionic equations. Okay, finally, we're going to look at our Kw. And we know that our self-ionization of water is going to be 2 waters in equilibrium with our hydronium and hydroxide. And Kw is equal to concentration of H3O plus times concentration of OH minus. And the thing about our self-ionization of water is that going this way, it's endothermic. And if you remember your equilibrium unit, if we increase the temperature, then your endothermic reaction will be affected more. So let's say we increase temperature, then our forward rate is going to be greater than our reverse rate. And we're going to shift to the right. So we're going to be forming more ions. So this goes up and this goes up if we increase temperature. And since our Kw is going to be these 2 ions multiplied together, increasing temperature increases these ions, right? In terms of concentration. So then our Kw will also go up. Okay, that's it. Those are just some main things that you might have missed. Make sure you still study your 3 note packages, and good luck on this very difficult test.